Good day. This is the presentation for paper 19 of SISAP 21, entitled Structural Intrinsic Dimensionality, and this is presented by myself, Stephane Marchand-Maillet, in co-authored with my colleague, Pedreira and Edgar Chavez. In this presentation, I will focus on the concept of local dimensionality, and this work is about proposing some new solutions to estimate and use it under the form of structural regression and the main contribution, structural intrinsic dimensionality. The practical motivation of that work is that we know that indexing fails with the increase of dimensionality. Essentially, with the increase of dimensionality, nearest neighbor search will downgrade to a linear scan of the data and forcing the search to visit all the points to find neighbors. And this is important and critical because any data analysis and learning relies on the fact on an efficient access of data and its neighbor for propagation or for averaging or whatever neighborhood operation you may think of. So the parallel question one can ask is how to quantify that degradation and how to combat that degradation in practice, essentially. There's been a lot of work made around this, and the solution generally taken is to go for approximate neighbor search and offering theoretical guarantees both in time and in precision, or in precision versus time, one could say. The nearest neighbor indexing theorems gives insight, theoretical insight on why this degradation appears. In fact, indexing is essentially about partitioning the space using, in the theorem, convex tiles with a certain granularity. So you sort of give a scale to the data, and the problem is that the interdistance, the entire object distance, become less than this granularity, including the distance from the query to its nearest neighbor, when the dimensionality increases. As a result, all the tiles need to be visited by the indexing in I-dimensional, so the indexing cannot be discriminative and cannot exclude any prior points. So finally, you end up with this linear scale. This is a very naive illustration in low dimension, because of course one cannot illustrate in I dimension because it's an I-dimensional phenomenon. In 2 dimensions, things go right. But essentially, what happens is that everything becomes equidistant. So you see that this granularity is the same as the interdistance between the point and the query, and every tile is hit by the query, and every tile needs to be visited, and none can be excluded. This equidistance comes as the classical phenomenon also known as concentration of distance or vanishing variance from a classical paper in indexing, essentially saying that the limit when the dimensionality increase of the variance of the distribution of distance relative to its mean tends to 0. This is very easily illustrated, again, classically, by the fact of sampling an m-dimensional cube with, for example, 3000 points, and drawing the histogram of the distance, the interpoint distance. And you see that in dimension 2, 12, 20, 30, and 50, the histogram will shift to higher mean, while its variance increases less than the mean. So the ratio tends to 0 eventually. And this is one facet of what has been called the curse of dimensionality. So this is all classical result, but we actually now question what is exactly dimensionality. Globally, this is rather clear. It's the number of orthogonal vectors that what can place in the basis. There are, of course, several other definitions, like the Hausdorff distance, the fractal dimension, or whatever the other dimension, global dimension you can think of. But locally, this is far less clear. Formally, there's unless you assume a uniform density, it is difficult to really give a definition of the local dimensionality. So we propose to not looking for a formal definition, but rather take it as any factor which drives the concentration of distance, or in practice, what we look for, anything that actually degrades the quality of our indexes. So again, there's been a number of work in that direction, and essentially relying on the expansion dimension. This is the family of local intrinsic dimensionality estimation. One can also look at angles, so more complex second order structures, one can say. And this has been discussed, for example, in the ABID paper of SISAP 2020. And also looking at reverse nearest neighbor in the space, and this relates to the so-called kissing number in the space. So all this is detailed in the paper, and I won't go in detail on these measures. But one conclusion we propose is that they all use the same information, which is the increase of volume of the hypersphere with respect to the increase of the radius of this hypersphere in the dimension. So since this relative increase depends on the dimension, by quantifying this increase empirically, essentially by counting the increase of number of points with respect to the increase of radius, one can estimate the law of increase, the rate of increase, and hence estimate the local dimensionality at point xi that is taken as a standard for this field. But essentially, all these measures go for isolated measurements. So by construction, these measurements are made locally at every point and not globally over the data set. So this is natural because it's local intrinsic dimensionality, but then there's no relationship between the dimensionality estimated at one point and the dimensionality is estimated at another point. So what is presented in this paper that statistical measures are applied to the histogram or to the result, and only some kind of a global local dimensionality is proposed. The dimensionality can vary locally and can not have the same value at one point and another point. So having a statistical overview of the local intrinsic dimensionality is misleading because it doesn't capture the local variation of the dimension. In this paper, we propose to use, in a stronger fashion, the neighboring structure to instruct us about the local dimensionality, and this is the base for the construction of structural intrinsic dimensionality. Our approach is to answer this question: can neighboring information be used to enforce the smoothness of local intrinsic dimensionality? So this is the first step, a structural regression, which I'll propose. And how can we derive dimensionality measurement directly from the neighborhood information that is captured over the data? So as a first step, we want to develop the idea that two neighboring points, xi, should receive close estimates for their local dimensionality, which we denote dim of xi. So basically, the dimensionality of xi and xj should be estimated, should receive the same value if these points actually lie close in the data space. This is some kind of natural idea of smoothness. And one way to enforce this would be to say that the dimensionality at one point xi is actually some kind of global average of the dimensionality of points in its neighborhood. This is essentially an ill-posed problem because it's translation invariant. You can easily convince you that if this is true for dim for a certain dimension, then if you add a constant value to every point, to the dimension of every point, this remains true. So what you need to do is to either fix the dimensionality of one point to fix the propagation of this information, or to start from an initial estimate at every point. And this is this latter solution that we take by proposing a structural regression which globally seeks the dimensionality at every point. So D is the value of the dimensionality, is a vector giving the value of the dimensionality at every point, and is initiated by some estimate, for example, the local intrinsic dimensionality that is captured by the technique proposed by Michael Hull and colleagues. And we do a regression. So we seek a value of dimensionality that is close, that stays close to this estimate at every point. So it's a mean square error on this estimate, plus enforces what we defined before this in a looser fashion, mean square estimate of the equation that we've seen in the previous slide. This is easily resolved by classical gradient descent with a learning rate eta, and we update an initial estimate, and we try to stay close, but enforce smoothness, because the assumption is that the initial estimate doesn't enforce smoothness because of the isolation nature of its computation. So this, the details are in the paper, but essentially this works well. Basically, we reduce the variance of the initial blue estimate at every point. So the data set is a data set composed of a cluster of one dimensionality, another cluster of points of another dimensionality, and another cluster of points of another dimensionality. This is, again, also to demonstrate the idea that dimensionality of the data set can vary from point to point. Here, the points are ordered so that they visit first the first cluster, and then the second cluster, and then the third cluster. And we see that the estimate given by the initial estimate, the local intrinsic dimensionality in this case, has a high variance, and our structural regression naturally reduces that variance and provides a better estimate of the dimensionality at every point. So basically, the variance really alleviate the regression really alleviate the variance. And here what we took is the influence, the weighting in the neighborhood, taken as this value, which is inspired essentially by the classical physical gravitational like model that are classically used in the, for example, spring model for points. So this shows that enforcing smoothness over the estimation, the local intrinsic dimensionality of a data set works. So you can impose smoothness. And this also shows, more importantly, that the local intrinsic dimensionality with the measuring the increase of volume against the increase of radius does not capture the whole information contained in the data. There's more to capture, and this is this information that is captured as the regression. And we can say that the regression actually adds some complementary information in the estimation of the local intrinsic dimensionality. So the second kind of step we want to take is to say, can this structural information that we bring by this enforcing the smoothness, can itself, just by itself, give an estimate of the dimensionality? So we start again with this idea of smoothness by the fact of a point being the average of the dimensionality of its neighboring point. And we look for a propagation, a bit like page rank-like algorithm, with the graph, the neighborhood graph, oriented neighborhood graph given by the classical distance graph, and do some propagation like a page rank-like algorithm. So every point instructs its neighbors to its dimensionality, and there's this propagation. So we do this propagation like a page rank-like algorithm. So we iterate, and we see that as a weighting, PageRank uses the degree. So basically, it spreads the information over the degree of its uniformly the degree over its neighbor. But here, so we reread this degree as a weighted sum, but weighted uniformly. But we need to generalize to account for the distance between the points, because in PageRank, if you consider the hyperlinks, every hyperlink is considered as the same distance 1. So there's no idea of a distance. It's just one click, essentially one step. Whereas we need to accommodate for the distance between the points, because our data lies at various distance in the space, and we need to reread this weighting scheme as a weighted distance that a weighting scheme that accommodates for the distance. For example, you can take this phi. If you take phi equal to 1, you end up with the same ranking, the same weighting as PageRank, whereas you can take, for example, an inverse of the distance, or what we showed previously in the regression is we took 1 over x squared, which would actually weight by the square distance, the inverse of the square distance between 2 points, or the exponential of the minus the square distance, Gaussian, like a Gaussian kernel or things like that. So this generalization allows for accommodating for the distance between data points, and we do the propagation. And we see also that this, with random initialization of the distance, converges with some information that also is correlated with the structure of our data set, because we really recognize the R cluster in our data set. And we see that this propagation alone, with no estimation of dimensionality whatsoever, actually can correlate with the structure, the dimensionality structure of our data set. And we also see that this goes hand in hand with the regression that enables the smoothing. But the smoothing actually affects less the mean than just the variance. So the conclusion of this is that this structural intrinsic dimensionality, which is the factor that is propagated over a PageRank algorithm, PageRank-like algorithm, on the neighborhood graph, can bring some proper estimation of the local intrinsic dimensionality while using the global structure, because we use the graph and we don't estimate the local dimensionality over simply every point independently. Everything is done on a propagation manner. So, of course, there's a lot of questions that arise from this approach, and we basically argue for the complementarity between the regression and the structural propagation, and we wish to enforce the idea that there's more to capture than pointwise local dimensionality estimate, and that the graph of neighborhood in structures contains this information of dimensionality. So we wish to work out extension, and this will be the aim of our future work. And this panel that is constructed for this propagation is actually the base for providing operational tools that, as we said, it's not just the idea of estimating the dimensionality, but also using this estimation to combat it, for example, through clustering or splitting the data set for retrieving some efficiency in the indexing of this data set. Because since the concentration of distance is a really deeply rooted statistical phenomenon, there's no hope to combat it as a whole. We need to do something like partition the data set or use indexing where possible, where the dimensionality of the data set is actually low, and just use linear scan where the dimensionality of the data set is obviously high. And this is what we proposed in SISAP 19. And this is another complementary work so that we can estimate better and rely on smoother estimation of local dimensionality. So thank you for your attention, and thank you for listening to this presentation. And I really encourage you to read more detail and discussion in our paper, and also I look forward to discussion at SISAP 21 in a few days.